spectacular. No one can yet predict exactly where lightning will strike next, but some rough predictions are now becoming possible, thanks to the work of Raul Lopez. Lopez and his team count lightning flashes using a network of sensitive detectors.
When we first started to get the data, we were overwhelmed by the amount of this data. In the past, researchers had been looking at just a handful of lightning flashes, maybe over several years, 100 or 200. And here we collected, in 1 year, we collected 750,000 flashes in just a limited area here in Colorado. So we were overwhelmed. I said, well, what do we do with it?
What Lopez and his colleagues did was to organize the data with a special kind of graph called a histogram, which is what we'll explore in this unit. We'll continue our look at distributions, which display the values taken by a variable. We'll learn that we can use histograms to represent distributions when we have substantial amounts of data. And we'll learn to examine histograms for qualities such as symmetry, outliers, gaps, and skewness.
Right in here.
The system of detectors set up by Lopez flooded his computers with data. One aspect of the lightning flashes particularly interested Lopez: the time of their occurrence. The challenge was to make sense of these numbers, to organize the data in a way that would reveal a pattern in when and where the lightning struck. To begin his analysis, he decided to look at when the first lightning flash of the day occurred. To see the distribution of time of first flash, he used a histogram, which is a special kind of bar chart. Here's how he did it. To simplify the task, Lopez counted how many first flashes fell in each hour of the day. Because the data was stored in a computer, the computer did the counting. Now we can draw a histogram to display the distribution. The horizontal scale is marked off in hours. The vertical scale is the number of days in which the first flash occurred at a given time. You can see that each bar represents 1 hour of the day. And as we said before, the height of the bar is the number of days in which the first flash fell in that hour. The striking feature of this distribution is its symmetry around the central bar representing time between 11 a.m. and noon. Of course, the two sides are not exact mirror images, but that's to be expected with real data. Another striking aspect of the histogram is how tightly the data cluster around the central bar. The range from 10 a.m. to 1 p.m. accounts for most of the observations. This data on first flashes clearly demonstrated that in the Colorado area under study, lightning storms never began at night. Instead, they almost always began within 1 or 2 hours of noon.
The interesting thing about these histograms showing the clustering was that, look, there's something irregular here, something that tends to occur very frequent during the summer. A lot of these days, the first flashes are tending to occur at a given time.
Lopez consulted with weather specialists, and they realized that the regularity of lightning flashes was linked to the rugged geography of Colorado. In summer, warm air from the plains hits the Rocky Mountains. The air cools, and storms build in a daily cycle regulated by the sun. Lopez and his colleagues also looked at the time of day when the maximum number of flashes occurred. They found a similar pattern. A peak showing that most days had the maximum number of lightning flashes between 4 and 5 in the afternoon, with a narrow spread of a few hours on either side. But this time there were also some outliers, points that fell outside the general pattern. Here, the outliers are cases where the maximum lightning flashes didn't occur until early morning. In this case, the outliers were not mistakes. They were clues that something unusual was happening.
When you look at the distribution of the maximum activity, you notice that there are some that were not clustering at all, but were occurring far away from the center. You immediately tend to think about outliers and why. Those are days where you have a very strong control by your weather systems. You might have had a late front coming in during the day or a very early front coming in during the day and overpowering the local influence, this influence that comes over and over every day that determines the clustering around a particular time.
All the lightning strikes are all concentrated in one area.
You can actually use the lightning in this case.
While the work by Lopez and his colleagues does not allow for predictions about exactly where and when lightning will strike, it is a big step forward to more general predictions.
I don't think we're at a stage where we can say that we can predict lightning, especially when it comes to predicting where it would actually hit. You see, that's a very major problem. But I think we're in a position now where we're starting to learn what are the factors that determine if a day is going to have a lot of lightning, little lightning, or be in between. I think we're at a position now where we can start saying, well, if we're going to have some lightning, probably is going to be occurring in this region of the mountains, and around the peak activity is going to occur around this time.
Making a histogram is straightforward once you have decided how to divide the observations into classes, such as we did with the lightning data. Remember that the classes of a histogram leave no space between them because they cover all values of the variable. It's also important that your classes be the same width. That's because we're representing counts with a histogram. If we varied the width of the bars, we could give a false impression that one bar was somehow bigger than another, even though they represented identical counts. Choosing the best way to divide your observations into equal classes requires good judgment. Hours of the day were clearly a good choice for constructing the lightning histogram, but it isn't always this easy. Suppose, for example, that we want to show how the number of cars passing our school varies during the morning rush hour. This is a lot like the lightning flashes. Every car, like every flash, appears at a certain time. Let's say we collect our data and want to present it with a histogram. How wide should our classes be? Should we graph the counts of cars in each hour? We can see from this histogram that the traffic peaks between 8 and 9, but that's not very precise. How about creating half-hour classes? That's better. How about 15-minute classes? Better yet. Now we can see that rush hour is at its worst between 8:45 and 9:15. That's information we couldn't have gotten from the other histograms because the class sizes were too large. Can we get even closer? What if we created 5-minute classes? All of a sudden, the peak is harder to see. There are too many peaks. As classes get too small, the number in each class begins to look the same. Unfortunately, trying different class widths takes a lot of time, so try to make a good choice first time around. Making histograms is one place where computers can help a lot. Computer software can make a choice of class size for us, and if we don't like the look of the histogram, we can just tell it to pick a different class size. Once we've constructed a histogram, we can immediately begin to get information from it. First, look for the overall pattern, and then look for deviations from that pattern, such as gaps or outliers. Two important types of overall pattern are symmetric and skewed. The histogram of the time of first lightning flashes was approximately symmetric. Here's a histogram that's clearly not symmetric. It shows the weekly wages of all workers. As you can see, most people earn modest incomes, while a few people are millionaires. When a histogram is lopsided like this, we say it is skewed in a particular direction. The thin end of a skewed distribution is called the tail. The direction of skew is determined by which side of the graph the tail is on. Since the tail of the income histogram is on the right, we say it is skewed to the right. Another thing to look for in the overall pattern of a histogram is spread. Some distributions, like the lightning data on first flashes, are tightly clustered, while other data, such as these data on the number of days that heart disease patients spend in the hospital, are much more spread out. In this unit, we've learned about histograms, one way to picture data so we can more quickly and easily understand them. We saw that histograms are useful when we have large sets of data that we can break into classes. And we learned that when making a histogram, we need to keep the class sizes equal. And be sure we're using class sizes that give us the most informative picture possible.